Okay, we can stop complaining about management now. So it will be a short lab week, but you do have to study for the quiz, so there's some outside of lab work to do. And the Lab 2 pre-lab will be due the following week. Lab 2 is also a 1-week lab, basically following the same schedule. So it'll give me time to get to Phoenix because I have a vaccination appointment down in Phoenix on Friday afternoon. Yay. Everybody's complaining because you can't get them in Flagstaff. You can get them in Phoenix if you're in the right group. You have to be a teacher or a medical person right now. My son, who's only like 31, is in the next group to get vaccinated because he works for the gas company. Some of the logic. What really matters when you're studying isn't the amount of time you put into it. If you're spending 3 hours on your homework, but we're watching a movie at the same time, all of that time isn't being really spent on task. You'll get more out of it if you actually single task something and concentrate and focus. You can actually get more out of your time and then have more free time later. They've proven that, even without Salvador Dali. Okay. This is part 2, advanced CMOS. This is stuff we haven't covered in 280. We're going to start out talking about the body effect and some little bit more device physics, and then talk about p-in junctions for a little while. And yeah, then the body effect comes in there somewhere. And then we'll talk about capacitance. And actually next class will be focused on how do you calculate those capacitances. We're going to find a lot of them are region of operation dependent or voltage dependent. If we have to include them in our circuit model, it's too much for a hand calculation. And this is why we love Mentor graphics on some days. And by the way, I do want to add this too. Did you notice that really irritating program in EE310, the simulator? It's called Model Sim. It was also built by Mentor Graphics. Okay, never mind. You'll learn to both love and hate Mentor Graphics as we go through this.
Well, because Mentor Graphics is almost like Multisim, just with a lot of extra steps.
Yeah, no, not Multisim, Model Sim.
Oh, whoops, my bad.
Yeah, it's different. It's the thing that you'll face that's kind of irritating in 310 is also a Mentor Graphics product. There's a lot of they actually build a lot of good EDA software. It's just kind of fussy to learn how to use.
Wait, does that mean Mentor Graphics is a subsidiary of Intel, or?
No. Mentor Graphics was a standalone company up until about 6 months ago, and they got bought by Siemens, the German company, because Siemens wants to integrate the simulation and the building and the FPGA stuff all into their circuit design. They want to have that all as being one process. But still, Mentor Graphics is selling. They still use that software as one of the industry standards for EDA tools for what makes it possible to put together chips that have billions of transistors in them and not drive yourself crazy.
So then, did Altera buy the Model Sim software off of them, and then before they got swallowed up by Intel?
Yeah, they're leasing it. So they're using it. Okay, so Altera's been bought by Intel, and Altera with the Quartus software, they didn't have a good digital simulator, so they bought it or leasing it because they want maintenance from Mentor Graphics for doing their digital simulation, because Mentor Graphics already had a digital simulator. In Fact, Model Sim can be integrated into that menographic suite, the PPN and all that stuff that you use in the 380 lab. But we're using it for schematic based simulation. But all those tools fit together in one suite, kind of. I was there back in the day in the 90s when they were trying to piece all this together. When we were first using it, I would have to write C programs to take the output from one menographics module, like the simulator, and feed it into the layout editor. So I'd have to write a C program to translate the file factor over. And the guys at Mentor were really interested in this because we were actually trying to build it all into a suite. And one of them, they hired one of the guys from our group, and that was one of his jobs, was to make sure that those handoffs happened automatically. And so he actually wrote a lot of the software for that. And we may have to go kidnap him someday and drag him back down here and explain menographics to us. I know where he's at. He's retired. He's up in Washington State. I miss Ken.
Oh, yay, Washington.
Yep. He's down near Longview for some reason. Okay, so the body effect. And this is where I trip a lot of people up on the exams. The body effect is always important, unless I tell you to ignore the body effect. So there'll be problems on there where I ask you to calculate the current through the transistor. And you do your standard 280 thing as you look at VD, VG, and VS, and you calculate the region of operation, and you go look up the threshold voltage on the front page, and you plug it into the right current equation and you calculate it, and yet you still come up with the wrong answer because you've neglected the body effect. If I tell you you can neglect it, you can, or if VBS is 0, you can neglect it, but otherwise it's important. It changes the threshold voltage of the transistor, and we'll talk about the details as we go through this, both from a physics standpoint and from a calculation standpoint as to how the threshold voltage changes. We'll talk about temperature effects a little bit. I want you to understand how important temperature is. It's one of the, when you design a circuit, you design it for room temperature, and then you put it in a car, and the car is warmer than room temperature. So now you have to, as an engineer, you're responsible for making sure the car will, your circuit will work in the car at that temperature. Or if it's a hot day in Phoenix, you want to make sure it still works. Or a cold day in Saskatchewan, you want to make sure your circuit still works. And by the way, it's a very cold day in Saskatchewan. It's minus 40 below right now. Colder than it is here. That's only Celsius. Well, it doesn't matter. Celsius. Okay. Now, go ahead, Michael. Okay.
Oh, no. I accidentally hit this button.
Okay. If we look at an inverter, inside the inverter, I've got a PMOS transistor and an NMOS transistor. We got to remember they're really 4 terminal devices. It's not just drain, gate, and source. It's drain, gate, source, and body. Now, normally what we do is we connect the body of NMOS transistors to the lowest voltage in the circuit. So we connect the body of the NMOS to ground. We connect the body of PMOS up to VDD. And you'll understand why in a minute. We'll go through that qualitatively. So here's my NMOS transistor. The body is here, and it is tied. It's going to be tied directly to ground, and it's tied directly to the source. Remember, I'm finger painting, so this is going to be kind of sloppy. Over here on the PMOS, I'm also tying the body directly to the source, but I'm going to tie those to VDD. Now, this is beautiful because the body to source voltage on both of these transistors here is 0. the magnitude of VBS equals 0. Okay, we can do that in an inverter. Now here comes the problem. I've only got one body tie, because remember, this is tied into the substrate of the device. It's universal for the whole chip. I can only pick one point to throw it, to tie it to. Here comes the problem. I've got a more complicated circuit. This is a NAND gate, because remember, this is on PMOS series is AND, so I've got a NAND gate. The bottom transistor here has the body and the source both tied to ground, but this transistor right here, the body is tied to ground. The source is at a different voltage than ground. So in this case, in that case, the magnitude of VBS does not equal 0. So I'm going to have a body effect. What's going to happen on a top level when I think of this is that if VBS is not 0, my threshold voltage of this transistor increases. And it's going to increase by enough to matter even when you're doing like hand calculations. Now these two transistors up here are okay. They've got their bodies tied to the source, so they're okay, but this is really the only one problem one. And Mentor Graphics will take care of that for you, thank goodness. This body, we call this VSB, is called the body bias. And what really matters is the magnitude of it. If the magnitude of VSB goes up, then the threshold voltage goes up. Okay. Now we're going to talk about diodes for a while. Now, what we know about a diode is here, and this will make sense eventually. There's the symbol of a diode. This is the P side, and this is the N side. And we know current flows pretty freely if I put a positive voltage on the P side, relative to the N side, then lots of current will flow through there. If I go the other way, and I put a positive voltage on this side and a negative voltage on this side, the current is going to approximately equal 0. It'll be a little bit of leakage current. There's an equation for this. Cheat a little bit. Oh yeah, that's right. I'm checking. And the equation for the current through the diode is ID equals some constant for the diode, IS, E to the positive voltage across the diode over VT. And VT is the old thing, it's the thing that equals about 25 millivolts, but changes with temperature. It's KT over Q, so it's highly temperature dependent. The T in there is the temperature in degrees Kelvin. So as the temperature goes up, the current goes up exponentially. Which is why we have to do all that temperature testing. If I draw a graph of the current, this equation describes it fairly well up until, you get, oh great. It doesn't like me drawing lines parallel to each other. I get an equation that looks like an exponential. This is ID versus VD. And that works fairly well until we get into reverse breakdown, which we never really talk about much, but this is called the Zener mode. And if you take a class in p-n junction physics or in semiconductor device physics, you'll learn all about that. There's the current, and when I physically build this device, what I'm going to do is I take a P diffusion and I build it next to an N diffusion. Well, the N type has a whole bunch of electrons in it, and the electrons are attracted to the positive charge in the P region. So some of the electrons are going to jump over that barrier and come over into the P side. If they get too far in the P side, what happens is they find a hole, and the hole in the electron, the electron fills the hole, and it becomes a neutral site. So all a hole is an absence of an electron. Now, some of the holes from the P side, some of those absences are going to be attracted to the negative charge over here. So I build up, oh great, finger cooperate or screen cooperate. I build up some positive charge on that side of the barrier. This is called the depletion region. Okay. If I have the diode sitting in the parts cabinet or lying on my desk, what's going to happen? There's current flowing through there all the time. The holes moving to the N side will be exactly canceled out from the opposite current moving to the other side. So these holes are moving over here at the same time, and the holes moving due to the difference in concentration and charge is called diffusion current. That is current due to a difference in charge. Drift current is due to an electric field. It's the normal, I put a voltage across something, I get current. So the concentration in charge builds up this depletion region. This depletion region has charge separated by a distance, which creates an electric field in this direction. So the current due to the electric field exactly cancels out the current due to the diffusion, as it has to, because you've got the diode just sitting on your desk. Okay. We're going to look at MOSFETs and see the diodes in there in a minute. But first, I think we got to talk about crystalline structures. Okay. Every solid crystal, and silicon is a solid crystal, has a crystalline structure associated with it. Silicon is in column 4 of the periodic table. And if you remember basic chemistry, all atoms want to have 8 valence electrons in those low states, because that gives them a full valence shell, which is very stable. Silicon has 4 valence electrons. So the way it gets to that stable state where it has 8 valence electrons is each silicon atom is going to form a bond, a single covalent bond with its 4 nearest neighbors. So now its 4 valence electrons are shared with one atom, and 4 different atoms are sharing their valence electrons with it. So it effectively has a full valence shell. Silicon wants to make 4 bonds. So it's going to do this by going into this tetrahedral structure, like we see right here, where it forms a tetrahedron, 1 silicon atom in the middle. The furthest apart the other atoms can get to each other is a tetrahedral, and that's why the silicon likes this. So there'll be 4 on the points of a tetrahedron surrounding it. Okay. That is the structure. And there is the picture, right? And we talked about that. What did that have to do with that? Okay. So this is the picture I was attempting to draw a few slides ago. I've got the holes over here are attracted to the electrons on the inside. So they jump over the barrier and they get this depletion region right here. And the electrons move over to the left side. This is going to create an electric field. because now I've got this charge separated by a distance. I'm going to have an E field. Make sure I get it in the right direction. I said that out loud. I have polarity issues. 1, 4. Yeah, the E field is pointing from, yeah, I got that right. The E field points from plus to minus. In addition, over here, I have another E field, and I have an E field here, and they're pointing in opposite directions. So there's 2 different junctions in there. This is how I understand electromagnetics, and I'm sorry, this is the simplified version. This is as much as I need to know. To get voltage, okay, voltage is in volts. Electric field is in units like volts per centimeter. We'll use centimeters since this is a semiconductor class. If I want to get voltage from E, what I do is I integrate, oh, come on. I integrate E dx. So if I have a constant electric field across a distance, the voltage induced would just be this electric field strength times the distance. Okay. Right here, I have a voltage going into a chunk of silicon. This is the plus side, this is the minus side. The E field is going to go from plus to minus. And if I flip this around and make the sign negative, this is the positive side, this is the negative side, and now my E field points in the other direction. It's just like electric field that you talk about in EE380, except it's confined within a region, and engineers have forced it to be linear because we'd rather just multiply electric field times distance than figure out this nonsense like you do in 364. Okay, sorry. I've taken a lot of EMAG too. I just haven't used it for a while. So I've got this electric field in the center here. It's across a distance. If I integrate that, I'm going to get a voltage, and that's what generates this barrier potential of a diode. When you calculate it, it comes out between 0.5 and 0.8 volts. If you're just ballparking things, most people for a silicon diode just say 0.7 of a volt. Okay, couple of things can happen here. I can put this diode into forward bias, and in forward bias, I'm going to put a positive voltage on the P side and a negative voltage on the N side. And the depletion region width is going to decrease. And because this region decreases, I have the same potential, but now it's in a shorter region. So when I integrate that, my barrier height is going to be lower. If the voltage barrier is lower there, more electrons can move across. Okay, lower barrier, more current. It's like the kindergarten looking version of microelectronics. I'm sorry, I gotta write with my finger. Okay. If we go, it's almost as bad writing with a stylus. I shouldn't laugh so much. If I go into reverse bias, that depletion width gets larger. I'm integrating the same electric field over a larger distance, so this V0 this barrier gets higher. It's no longer called V0, but we'll just, I get a higher barrier. It's easier to write V0, and I get less current. So I put a forward voltage across there, I get a lot of current. I put a reverse voltage across there, I'm not going to get a lot of current, and mostly leakage current in the range of like nanoamps or so. Okay. That's what I just said. Except for here, this is the barrier height with no voltage across it. It increases by, the barrier height increases by whatever positive voltage I put across it in the negative direction. So this is in reverse bias. I increase the barrier. In forward bias, I decrease the barrier by that same height. Okay. Inside a MOSFET, look at this. I've got an N region here. I've got a P-type substrate. It's a diode, whether we intended it to be a diode or not. The P-type substrate, and this is NMOS, remember, I want to tie this to the lowest potential in the circuit, so I'm grounding that P substrate, which means this region at the source has got to be either zero bias across there or a negative bias across there. I put a positive voltage on S, I'm reverse biasing this PN junction right here. As I reverse bias it, this depletion region is going to still exist, but more reverse bias is going to give me a larger depletion region. So the higher the voltage at S gets, let's just do it this way. If S increases, then the depletion width will also increase. This fixed charge in the depletion region, okay, this is a P-type substrate, so I'm going to have negative charge in there. All this negative charge builds up, and it gives me less charge available to produce a channel. So what's going to happen is the threshold voltage will also increase. We'll figure out a way to do that quantitatively in a minute, but you get the idea. The substrate voltage is fixed, it's tied to ground. The source the body voltage is the substrate voltage. This is the body. If the source voltage changes above ground, I'm going to widen the depletion region. I'm going to increase the amount of charge accumulated in there. I'm going to have less charge to form a channel. The threshold voltage goes up, and it goes up by a fair amount. Okay. Oh, guys. It's time to wake up. Another one of Dr. Brower's things. This is actually a book, and Daniel Goleman's pretty famous. He's the guy who came up with the multiple personality disorder. Wait, no. The multiple intelligences thing of learning theory, where some people are more tactile learners, some people learn visually, some people learn auditorially. He's a big researcher into educational, what are the methods of education that work best for everyone. And one thing he found that worked really good for everyone is that multitasking doesn't work. Being able to focus on a single task and maintain that focus till you get to a reasonable level of completion on that task turned out to be the #1 predictor of people's financial success later in life. So multitasking is a myth. You got to be able to learn how to focus. This is why I love engineering. I can sit down with an engineering problem and block out the whole world for 30 or 40 minutes until I get it figured out. Very relaxing for me. Sit with it, get all the details in your head. It will help you to focus. And that ability to, I mean, I'm a much better thinker, long-term cognitive thinker now than I was when I was your age. And a lot of that is just practice, sitting down and focusing and doing these types of problems, or focusing on one problem at a time. And it really does work. And that's a book. Now we'll go back to engineering. That was your educational theory blurb for the day. Reverse bias, we just said, has a wider depletion region. I just made you multitask in the middle of me telling you to focus. Okay. Compared to the zero bias depletion region, it's more area, so there's more charge. The threshold voltage increases, and we just talked about this. Now, when you look at your data sheets, like on the front page of your exam, or at the TSMC 0.018 file that has all those parameters in there, it doesn't give you VT, it doesn't give you V threshold, it gives you something called VT0. And what VT0 is for that transistor is the actual threshold voltage of the N transistor when evaluated where VBS equals 0. I can't finish that. Any value of VBS above that is going to give you a higher threshold voltage. And you can calculate that. And I said that, I'm sorry, I'm going to jump topic after I just told you to focus. The TSMC file that you see, it comes from a process from a company called TSMC, the Taiwan Semiconductor Manufacturing Corporation. Right now, they are one of 2 companies that are still pushing the envelope to make smaller and smaller transistors. Production state of the art right now is 5 nanometers, although Samsung is in pre-production on 3 nanometers, and they are doing research into 1 nanometer transistors. TSMC is the only company that can really compete with them. They're building their state-of-the-art 5 nanometer production line in Phoenix. I have gotten invited to a meeting with these guys because they want to hire 300 new grads this year, electrical engineers. And so for you guys, this is great. You're graduating at a really good time. If they're hiring 300 new grads, there's probably not that many new grads in electrical engineering graduating this year in Arizona, all the way across the board. Other people who are trying to hire new grads are going to be competitive. So you want to be out there with the skills that you need to be able to get those top tier first jobs. It will help you all along, and it'll be way more fun for you than doing other things. Okay, I'm meeting with them first week in February to talk about how they can hire you people. What kind of skills they need to see too. So here is the equation for the actual threshold voltage. It equals VT0. I can get that off of that parameter. I can get that off of the TSMC 0.18, the thingy file, or the front page of your exam. Gamma is another thing I can generally get off of that, whatchamacallit, the sheet. Phi F is another parameter of the transistor that you can get off of the transistor data, this one here. The only thing that really changes is this magnitude of VSB. And whether I say magnitude of VSB or VBS, it doesn't matter because one's just the VSB is just the negative of VBS. We get this equation. We can actually go through, look up these numbers, figure out what VSB is by looking at the circuit, and calculate the new threshold voltage that will give you a much more accurate value of the current. Now, I don't want to plot this because it's plotted on the next slide. If I had something that was linear, we'll call this A. This is A here. That's a linear graph. That's not what this graph looks like. If I had something where VT depended upon the square of VSB, we'll call this B. You'll get something that's parabolic like this. If you plot this curve, the one for the actual equation, what you get is this curve right here. You can see if I start out with a threshold voltage of 0.4 of a volt, I can easily like push up 5.55 volts, have a 30% change in threshold voltage, which is, you get to square that. So you get a much higher percentage change in current. Body effect always matters. And you can calculate how big it is using that equation. Just be careful with your units. So, already. I was just talking about this today in 490. All right, let's start out here. The source voltage is at 0 volts at time t equals 0. I've got the gate at 1.8, so VGS is 1.8. It's not in cutoff. To check and see if it's in saturation, I say, is VDS greater than VGS minus VT? VDS is 1.8. Is that greater than 1.8 minus VT? Yes. It's in saturation. That's telling us current is flowing. Where is the current flowing? It's going from drain to source. The only place it can go is charging up this capacitor. As that capacitor charges up, I charges C. As the I charges that C up, Q equals CV, VS is going to increase. So VS increases. Eventually you'll get to the point where VGS is just sitting right at VT. This voltage goes up, this transistor current starts to go down. Usually where transistors settle, when they don't have to drive any current, they will settle in the state where it's barely on, where the default, if you have to guess what the voltage across the gate to source of a transistor is, V threshold is the best guess, because it'll keep VGS at VT to keep the transistor on, but it won't be driving any current. What does that mean for losing a threshold? That means the maximum voltage that I can get VS to is 1.8 VDD minus VTH will be VS max. I cannot pull it all the way up to VDD. I have VDD on this side. The highest voltage I can get on this side is VDD minus a threshold. We will talk more about this, much more about this when we get to past transistor logic in the next week or two. Okay. That's just a preview. Now, where does this remember we had this equation right here. There's this gamma in here. Gamma is usually given on the data sheets from the manufacturer, but if you're someone working at TSMC, you're going to want to know more about the details of what causes gamma to be higher or lower. So there is an equation, an expression for gamma right here. 2 times the charge on an electron. I can't change the charge on an electron. I want this number to be smaller so it has a less of a body effect. Na is the doping in the P region. So it's the doping of the substrate. I have control over that. Epsilon S is the dielectric strength of the semiconductor. No control unless I change the materials, and it will be silicon. And Cox. And Cox depends upon the material of this gate electrode. So you've got a couple of handles here you can tweak to change gamma if you need to. Do we want to go through and actually do that calculation? Probably not. How much time do we have? We've got half an hour. We've got a lot of slides to do. We are on number 7. So you could go through and do the calculation with these numbers, and I've got it in the slide solution, so if we need to know that, it's in there. I'm coming up with 860 nanofarads per centimeter squared. That's Cox. Gamma is 0.2117. And the units are square root of volts. Okay. So once the process is set, you can't change gamma, but if you're a processing guy, you can mess around with it and change it a little bit within the parameters of your materials. For PMOS, guess what? This same equation works. Exact same equation for calculating VTP. The difference is this is a negative number and this is a negative number. So no matter what, your instead of VTP, VTN got larger, right? VTP, the body effect is going to cause this to get more negative. Which means it's going to take more voltage to turn it on, more voltage to turn it on. So same effect with PMOS transistors. That doesn't change. Temperature effects. You don't get enough of this in school, other than me, Randy. One of the really easy job, or not an easy job, but a job to give a new fresh out engineer is take the circuit that's already been designed or this process and see what happens with temperature. So I'm going to freeze it. I actually put it in a refrigerator. They have special refrigerative devices for this. I'm going to heat it up. And I'm going to see if the circuit or if this process is still working. Remember, the current through a diode exponentially depends upon temperature. All of the MOSFET current equations change with temperature too. The most basic effects that we can see that are easy to describe, as the temperature increases, the VT also increases, which would cause ID to go down. But as the temperature increases, K prime will increase, which would cause ID to go up. Turns out the K prime effect, the transconductance effect, is stronger. So overall, ID goes up. Now, I want you to think about this for a minute. You'll realize how big of a problem this can become. The temperature increases, so ID increases. When ID increases, the power dissipation increases, which generates more heat, which causes the temperature to go up, which causes ID to go up. You can get into the situation called thermal runaway. And this is what's causing it. You just get to the point where the temperature is going up so high that I am recording. Fire is fun. Yes, fire is fun, Amelia. I agree, but there can be an extreme on this. I'll tell you a fire is not fun story. So it can go up and it can actually damage your chip, let the smoke out, and it doesn't work anymore. I knew someone who was involved in patent law. This was enough years ago, I can tell this story now. Boeing had this battery, this whatchamacallit, lithium ion battery that they were buying from this company that was being tested in Tucson. And I don't know if you guys remember or not, but there was a big deal where they grounded a bunch of Boeing airplanes because these batteries were catching on fire. Okay. About a year or two before this, the company in Japan that developed this battery sent a prototype to a test facility down in Tucson. And the test facility got the battery in and they plugged it into the wall. And the fire that happened afterwards was big enough that it destroyed the whole building. And there's lawsuits going back and forth between the Japanese company and the Tucson company as who's to blame for the fire. The same battery ended up in the Boeing airplane and grounded them for a while. Yeah, I don't know how it got resolved. With a lot of lawyers getting a lot of money. Okay. So power dissipation, big deal. It can permanently destroy your chips. You want to keep an eye on it. This is why you need to use heat sinks and all that good stuff. As ID goes up, the power goes up. Delays go down, but it's not necessarily a good thing. Normally, when you buy any packaged integrated circuit, you're buying it for a set temperature range. And they commercial 0 to 70 degrees C. It won't last in a winter day in Canada. It'll last down in Phoenix. Industrial, this is for something like automotive, or where you're in an environment where there's a lot of heat, or you may be not well heated at all. -40 to 85 degrees C. -40 C is the same as -40 F. I know, I've been there. And military has the highest temperature range, but they're going to charge you more for that. Generally, it's more testing for the military parts and more testing for the commercial parts, and they put some other stuff on there that kind of keeps the heat down. But most of the time, for most applications, this is what you're getting. If it goes above 70 C, you stand a really good chance of your chip melting. Yes, -40 F equals -40 C. I'm a good Canadian, I know that. Or I pretend to be Canadian. Well, I'm Canadian whenever I want to be Canadian. Yeah. And I've seen it down as far as -56 F, which is about -50 C. There is a crossover point because they're two lines. If you plot degrees Fahrenheit versus degrees Celsius, they have different slopes, so the lines do intersect, and they intersect at -40 C. No, it's 40. I know that because it hit -40 C in Saskatchewan today, and I had a friend complaining about it. It's only, tonight it's going to get to minus 20 C here. It sounds colder, which is about 0 degrees Fahrenheit. Yeah. I claim to be Canadian. I'm sort of from Atlanta too. My family, the family that I have left is mostly in Canada. Capacitance, we want to get to this. And I've got, there's another family too that's almost like family, but we're not really related. We're going to look at how they actually start to make this. Knowing a few steps might help you on your TSMC interview. We're going to look at calculating these capacitances, and we'll finish this up on the next class. But we'll get this started here. Okay, I start out and I buy a silicon wafer. You can buy the wafers from a company there. I believe they're made mostly in France. There's different things they can do. This is just basically a P-doped substrate. You can buy it P-doped or N-doped, whatever you want. And it comes in a flat little circular thing. Silicon dioxide is a native oxide to silicon. If you leave silicon out in room air, it will oxidize and create its own little layer of silicon dioxide all around it. It's really easy to grow. A lot of time, if you want to prevent that, you have to store these devices in a cabinet that is in a nitrogen environment to keep all the oxygen out. So you start out with this, and the first step in my process is probably going to be to form the N wells. So to get the N wells, I'm going to take the P-type substrate and I'm going to put a whole bunch of N-type ions. I'm going to bombard it with that and create these N wells. But I don't want N wells everywhere. So I put this little pink stuff on here, and it's not really pink, and this is photoresist. And basically I put it all over there and I etch patterns on there, and it's basically using photographic techniques miniaturized down to the nanoscale region to be able to put this resist where I don't want N wells. And once I put that on there, I can bombard the whole chip, and I don't have to do this as exactingly at this point. I bombard the whole chip with this is going to be N-type atoms. N-type atoms like phosphorus, wow, which are going to give me extra electrons, and they're only going to go through in the region where I want the N well. And then I can remove this photoresist layer, and I have an N well built inside a P-type substrate. So that is the start of fabrication. I was a device physics person, but I was a theorist because that was what was fun. I have this weird mixture of very theoretical device physics and very hands-on electrical engineering. I should learn the parts in between, learn some more physics. Okay, I've got the N well in there. Now my next step is I've got transistors in here. I'm going to build transistors across here. I don't want the transistors leaking into each other. So I'm going to put a really thick oxide in this region right here. And we'll call that field oxide. That name will pop up a little bit later. And this is region, and this may be the transistor 1, and this is transistor 2. And I don't want these two transistors to have current flowing between them. I want to be able to control how current flows by connecting metal to them on other layers. So I want to put oxides which are very highly resistive in between these transistors. So I'm going to put another photoresist down, and this one's going to tell me every place that I don't want field oxide is where I put that resist down. Then I bombard it with more ions to create a channel stop implant. And in this region, I get something called FOX, which stands for field oxide. It's a very thick, very highly resistive layer. So now I can build transistor 1 in this region and transistor 2 in this region without a lot of electrons moving back and forth between them. So that is the channel stop implant. And there will be more to this story cartoon of processing as we go through this class. And we're almost done. Wow. Okay. Capacitance. Remember, you've seen this one before. I've got the gate to source capacitance, the gate to drain capacitances. All these capacitors have to be charged every time my input changes from 0 to VDD and discharged the other way. All of these capacitances are region dependent, their values, and their voltage, and some of them are voltage dependent. So it's really difficult. You can estimate what the delays are, and I think you get to do that in the lab 2 pre-lab based on the equations in Cedar-Smith, but you're not going to get a very accurate answer, because what I have to do to actually do this right, and this is what Mentor Graphics does, is it'll take this voltage and it'll change it by some little small incremental step, and then it goes and calculates what all those capacitors are, and then calculates all the voltages. Then it ups this a tiny little bit, and it does this all again, and it's doing so many repetitive calculations to get there. Doing that by hand would drive you crazy. Yeah, okay, the point of the slide. When I want to discharge these capacitors, when I want to pull them closer to ground, Q1, these NMOS transistors pull down. So the NMOS discharges everything. To pull them up, to charge them closer to VDD, I have to use these PMOS transistors. PMOS charges. The PMOS are slower. They conduct less current because the holes move slower, and they're less conductive because they're all bound to electrons. So to make up for that difference, generally I make the PMOS transistors 2 to 2.5 times bigger on W over L. So I make the W's twice as big to compensate for that. That way I can charge at the same rate that I'm discharging. Okay, all these capacitors have names, and they're based upon which 2 terminals they're between. This is the gate, this is the drain, this is the source down here, and this is the body. And so B would be called C, gate to drain. And the way you decide which, I could have called it drain to gate, but the general convention is the gate comes first. Pretend I wrote first, and the body comes last. This is the kindergarten view of microelectronics, because we're finger painting. So all those capacitors have names. We've been through that before. I have time, and you can figure out what those are.
Julie, did you say so? The B gate is capacitor gate to drain, was it?
This B capacitor right here would be C, gate to drain, because it's going between the gate to drain. Yeah.
Okay, I think the arrows point at C, gate to source, but I could.
No, the drain's up at the top because this is a NMOS transistor.
Okay.
C would be gate to source, because that would be the source down there. It's got the arrow.
All right, thank you.
Okay, no problem. Okay. Yeah, done. So any questions? I will do roll through the Zoom login thingy because I don't have my sheets with me. Start the homework whenever the homework's due. Always start the homework early in this class so you have a chance to ask questions. Some things aren't so clear. Some things are, you just, there's some things I just need to explain to you. I can't tell you everything in class. That's part of the reason why I like being in lab too, is it gives me one more opportunity to be able to explain things to you. And anything involving mentor graphics takes a lot of explaining. It's a weird program, but all EDA tools are weird. There's a girl who graduated this last not too long ago, last couple of months, had a job interview down at Microchip, and the job she was interviewing for was an actual design engineering job, which is pretty impressive coming in, but she was a really good student, pretty impressive coming out of college. And she sent me an email and said, well, this is the job they want me to do, and they want me to use all these cadence tools, and I don't even know what they're talking about. And she's mentioning all these tool names and everything. And I just came back and said, okay, this is what you do. You tell them you've used Mentor Graphics, and you've used the equivalent tool to the tool they want you to know in Cadence in Mentor Graphics. And once you've learned Mentor Graphics, nothing else is horrible again. No other EDA tool can daunt you again. So the fact that she had used similar tools really helped her to get the job and to get the interview and get the second interview and the third interview and all that stuff. And then I explained to her, I kind of explained to her in terms of what she learned in college, what the tools were and what she'd be doing. And she knew a lot more than she thought she did. And just translating that language really helped it out. But there's a lot of things we do in these classes that are industry standard, that are the way people really work. A lot of people, okay, take somebody like me. I'm learning FPGA design again. I'm taking 310. I'm embarrassed. I haven't done FPGA design for 20 years. But I was a circuit designer, and that meant when you get to a certain level, you're designing integrated circuits, you're designing the circuits inside the package, you're putting them on a printed circuit board, and then you're designing the interconnects between that circuit that you designed and other circuits and getting the whole signal chain going. This is what I did. And you're going from transistor level all the way up. You don't necessarily always just get to be an FPGA designer or get to be an IC designer. Sometimes you have to look at the problem in front of you and decide what's the best solution for that problem, and then learn that skill. And that's why I am learning Verilog now, or attempting to learn Verilog. Is because I have a problem in the lab that I want to solve with an FPGA, and there isn't anybody around who has the right skills to do it, so I'm going to do it myself. But you'll always be learning as an engineer. It's fun, and the more you're willing to take on and the more different skills you're willing to learn, the more valuable you will be. It'll give you career longevity, and it'll give you more money if that's what you're looking for. Or if you're like me, it'll give you more fun work to do, which when that becomes, if you're the type of person that's more important to, you'll get to do more varied work and get to work on some more exciting projects. So it's all up to you what you want to do with this. The world's wide open right now because there's 300 new, they're hiring tens of thousands of people, which means you got a double E degree. You're nearly golden this year, okay? It's a good time to be a double E. Any questions other than me ranting about jobs? Or you can ask questions about me ranting about jobs. Okay, it's dead. I will let you guys go, or I'll stop recording, and then we can talk about management again. Stop share. Stop recording.